A bobsleigh is a great example of the motion described in physics. Running on ice, friction is minimized, and the aerodynamic shape also reduces any effects of drag. The motion is essentially without any hindrance. As the run proceeds, the bobsleigh is more and more accelerated and the velocity increases. This presentation discusses the calculus definition of displacement, velocity, and acceleration, and how these three quantities relate to each other. The name kinematics of this field of mechanics derives from the Greek word kinema, which means motion in English. It is spelled in Greek kappa, iota, nu, eta, mu, and alpha. The top diagram shows a measurement of the magnitude of velocity, the speed of a bobsleigh, as that speed increases with the position along the track. One can identify parts of the curve where the velocity increases with position. We call this accelerated motion. And one can also see that in some parts of the curve the velocity is constant, is flat. We call that uniform, constant motion. This is particularly obvious at around 200 meters, where the ice canal must be horizontal. Similarly, between 600 and 800 meters, the velocity is almost constant, and we can interpret that as uniform motion, where little or no acceleration takes place. In contrast, at about 1000 meters, the curve is steep, and considerable acceleration must occur before the bobsleigh reaches its maximum speed of about 130 kilometers per hour. As with all mechanics, the field of kinematics rests firmly on Newton's three postulated laws that underpin all reasoning in mechanics. These three laws are expressed here mathematically. Newton's first law states if there is no external force F, then the velocity of a mass will either be zero, the mass will be at rest, or the velocity will be constant in magnitude and direction. This is what we call uniform motion at constant speed. This first law is also known as the inertia principle, which is depicted by the cartoon. The motorbike hits the wall, a force acts on it, it stops. No force acts on the rider. Because of his inertial mass, he continues to move on across the wall with the original speed v. Newton's second law states that if there is a net force F acting on a mass m, which is constant, then that will induce a momentum change. Since momentum is mass times velocity and the mass is constant, the differentiation only acts on the velocity. Since velocity differentiated with respect to time is equal to acceleration, the force equals mass times acceleration. F equals ma. The cartoon on the right depicts this second law. We imagine the box itself as a point mass, as we do with all objects in kinematics. And the girl pushes this box, this point mass, with a net force, which will then accelerate the box. The third cartoon, with the rock being pulled by the earth and the rock pulling earth, depicts Newton's third law, which is the actio equals reactio law. If a force acts from one body onto another, there is always an anti-equal force that acts from the other body onto the first. Importantly, and that is often misunderstood, the two forces form an action-reaction pair, with the two forces acting at two different points. They never act at the same point. The third law relates entirely to forces. Thus, it is not particularly important in kinematics. Kinematics rests firmly on the first two laws by Newton, and to appreciate the meaning of these laws, the quantities that they discuss, such as velocity v and acceleration a, and the mathematical formalisms that relate these quantities, such as in particular the time differentiation d over dt, need to be introduced and defined. This is the program of kinematics. What is time t? Time is an apparent feature of our world that everyone understands as progressing forward and in a uniform fashion. That's all that classical mechanics says about time. This intuitive understanding of time was challenged by Einstein correctly in 1905. However, within the limits of classical mechanics, which is most of our world, including space travel, this view of time is sufficient. Mathematically, time is a scalar. A scalar is a quantity that is completely specified by a single numeral and does not contain directional information. This is in contrast to the quantity vector, which we'll define in a moment. We are familiar with another scalar quantity, that is the scalar quantity of mass, m. In mechanics, it is often convenient and sensible to imagine the total mass of an object m to be concentrated at its center. The mass that appears in Newton's second law is thought of as such a point mass. Two examples are shown. The complex object bobsleigh, which has a certain mass m bob, is viewed as concentrated in its center of mass as m bob. Similarly, the center of mass of a car represents this very complex object. And the same concept can be applied to many other objects that are in motion. This is the very powerful logical reduction which makes the mathematical treatment of motion in kinematics possible. We note that all other quantities in Newton's laws are vectors. This is because mechanics takes place in our world, that we experience as a three-dimensional space with three directions, straight, sideward and up, at right angles to each other. That's our world. This is best represented by a Cartesian coordinate system, named after René Descartes, who lived from 1596 to 1650, just before Newton. A Cartesian coordinate system has three axes, x, y, and z, and by convention they are drawn in a right-handed sense. So drawing them as indicated next to the Cartesian coordinate system in a left-handed sense is not correct. This mistake doesn't have any immediate consequences in kinematics, however causes some fundamental problems in other areas of physics. Cartesian coordinate systems have to be right-handed. With space represented by a coordinate system, it is possible to define a vector. Vectors can be written down in different ways. They can be written down graphically, as an arrow with a direction and an endpoint where the vector acts, and the length representing the magnitude of the vector. Vectors can, however, also be written down mathematically using different types of symbols. There can be an arrow on top of the quantity, there can be a bold symbol, there can be a squiggle underlining the letter representing the quantity. All these notations are equivalent, and there is no fundamental difference between them. A vector can also be represented by its components. Again, these components can be written down in different ways. A velocity vector might have the components vx, vy, and vz, which can be written in a column or in a row, separated by commas. A further way of representing the vector is using unit vectors, I, j, and k, that point into the three directions of the Cartesian coordinate systems. In this representation, the Vx is in front of the I unit vector, pointing in x direction, the Vy is in front of the j unit vector, pointing in y direction, and the Vz is in front of the k unit vector, pointing into the z direction. The notation in Newton's laws that I stated earlier indicates that velocity v, momentum p, acceleration a, and force F are all vectors. This means all four of these quantities have a directional quality, and they can be represented by their three components as shown in the cartoon for the acceleration vector. The black vector is the actual acceleration vector pointing towards us, and the three grey vectors ax, ay, and az are its three components aligned with the three unit vectors I, j, and k. Note that the coordinate system has a right-handed sense. The directional quality of velocity is immediately obvious. Having velocity allows us to proceed over some distance. However, we can do this in a direction of our choice. We can go to the left, we can go to the right, we might even go backwards. This directional quality of velocity is represented mathematically by velocity being a vector. In regard to force F, I might consider that a force can push me forward, or it can push me backward. It has directional quality. If the push is along the x-axis, a forward push would be represented in component notation as 10 Newton in the x direction and 0 Newton in the other two directions. In contrast, the backward push would have a minus 10 Newton component in the x direction. It is clear that a proper understanding of mechanics requires knowledge of vector algebra. In Newton's second law, velocity is differentiated with respect to time. F equals mass times time differential of velocity. This demonstrates that a proper understanding of mechanics requires knowledge of calculus. The diagram with y plotted versus x shows a blue function. For a point x equals a second line is indicated, which is an approximation of the slope of that function between a and a plus h. This approximate slope is given by f of a plus h minus f of a divided by h. The limit of this ratio, with h tending to 0, is equal to the tangent to the blue curve at the point x equal a. This we call a derivative. Such a derivative is also shown for the larger blue curve underneath. The tangent line represents the slope of the function at the point. We can thus conclude that in Newton's second law, the external force is related to the slope of the velocity curve when plotted as a function of time. Summarizing, one may say that Newton's third law, which relates entirely to force, is not relevant to kinematics. This is discussed within dynamics, another discipline of physics. Kinematics discusses Newton's first and second laws. The inertia principle, which relates to uniform motion, as for example experienced by the Voyager spacecraft that has left our solar system and is far away from any attractive planets. And the second law, that relates to accelerated motion, as for example performed by a bobsleigh running down the ice canal. Since all objects are represented by point masses that are considered constant, the mass cancels in this equation, and it simplifies within kinematics as acceleration is equal to the time differential of velocity. Since this equation relates two quantities that are associated with motion, acceleration and velocity, this equation is also often referred to as an equation of motion. Motion is about moving from one position to another. In order to quantify this mathematically, it is therefore necessary to define a position vector r. It is quite instructive to use the bobsleigh example to look at the concept of position vector. The sketch shows a three-dimensional Cartesian coordinate system with the axes graduated in units of meter in the x, y, and z direction. The red curve shows schematically the ice track that the bob with the mass m runs down. The vector r1, which sits entirely on the y-axis, defines the start position of the bob. It has the coordinates 0, 500, 0 meters. The 500 meters represent the y component of this vector. Since the other two components are 0, we say that the vector does not have x and z components. After some time, the bobsleigh has moved to position 2, which is identified by position vector r2. This vector has the components 300 meters, 100 meters, and 100 meters. It points somewhat diagonally into the coordinate system and has components in all three directions. At the finish, the position of the bobsleigh is identified by vector r3, with the component 550 meters, 0, and 300 meters. Since this vector does not have a y component, it lies in the xz plane of the coordinate system. The straight line between two positions 1 and 2 is considered the displacement between those two positions. That's shown in the sketch here as the vector delta r21. The vector r21, the displacement, is calculated as the difference between position vector r2 and position vector r1. In this case, it is equal to 300, 100, 100 meters minus 0, 500, 0 meters, which gives us a displacement vector of 300, minus 400 and 100 meters. Note that this is a vector difference and that the displacement should not be confused with the distance L, which is the actual distance covered by the bob. Since the track is curved, in this case the distance L is much longer than the magnitude of the displacement vector. In kinematics, positions are defined by position vectors, and the displacement between those positions is considered in the calculation of velocity and acceleration. The question arises how the velocity of an object, such as a bob, is defined, so that it can be consistently applied in three-dimensional space. Intuitively, we understand the ratio of track length, for example from 1 to 2, in the case of the bobsleigh, divided by the time taken to go from 1 to 2, which is equal to track length L divided by delta t. Intuitively, we understand this as the average speed over that distance. This is a quantity that is certainly relevant to the sports competitors. However, speed is a scalar, not a vector, and it is not convenient in physics since the length L is curved. An alternative is to use the displacement vector delta r and define an average velocity v average as the ratio of the displacement vector divided by the time interval delta t. This has the advantage that delta r, the displacement, is a straight distance. Furthermore, dividing the displacement vector by the time interval delta t translates into a velocity vector, and that takes into account the directional quality of velocity. Average velocity is useful, but it's not uniquely defined because the magnitude and direction of the average velocity vector depend on the choice of start and finish of the displacement. The solution to this problem is to use calculus, as first discussed by Newton, and introduce the concept of instantaneous velocity. The sketch illustrates the procedure with the track of the bobsleigh, or more generally, a trajectory indicated in red. In blue, several position vectors are shown as r1, r1 prime, r1 double prime, r1 triple prime, and so on. They tend to approach closer and closer the second position vector r2. This iterative process is described in calculus using the limit. In this case, the time difference delta t tends to 0. As delta t tends to 0, position vector r1 becomes position vector r2, and the difference, shown in green, becomes smaller and smaller. The difference is the displacement vector, r2 minus r1. In the limit, the ratio of displacement and time interval becomes the slope of the trajectory at point r2, which is indicated by the tangent to the trajectory at that point. We call this limit the time derivative of the position r, and define it as the instantaneous velocity for the position r at the time t. The average velocity, which depends on the choice of position 1 and 2, is thus converted into an instantaneous velocity that is uniquely defined for position r and time t. Appreciating this complex procedure in 3 dimensions is quite challenging. It is therefore instructive to first look at this situation in 1 dimension. This is possible because the mathematical formalism is unchanged. That is illustrated here. The similarity can be understood by writing the time derivative of position in components. In 3 components, the position vector may have the components x, y, and z. Each component is differentiated independently to give dx on dt is equal to the component vx of the velocity vector, dy on dt is equal to the vy component of the velocity vector, and dz on dt giving the vz component of the velocity vector. Many kinematics problems can be described in 2 dimensions, and in this case, the time derivative of position is dx on dt is the vx component of the velocity vector, and dy on dt is the vy component of the velocity vector. In 1 dimension, only 1 component is left. dx on dt is equal to the instantaneous velocity. Shown in brackets is Newton's original notation using a dot to indicate the time differential. Because of its brevity, this notation is still quite common in modern textbooks. It has exactly the same meaning as saying dx on dt. In one dimension, both position and velocity become effectively scalars, and their directions, forward or backward, are expressed by the sign plus or minus. With a sound definition of instantaneous velocity, we can now discuss one-dimensional motions. The first example on the top left is a trivial example, a point mass m at rest. In this case, the position-time diagram just shows a constant line at the position x0, the rest position of the point mass. Since the position x is constant with time, the time derivative of x is 0, consistent with the instantaneous velocity being 0, which is expected for a particle at rest. Below the position-time diagram for a point mass that is in uniform motion. That means its position changes uniformly with time, indicated by the sloping line in the graph. Mathematically, the position is given by a constant x0, the original position of the point mass, plus a constant velocity times t, v0 times t, which accounts for the sloping of the line. If we differentiate this function, we obtain for the velocity dx on dt that it is a constant v0. This is indeed expected from the inertia principle that states that a mass in uniform motion should have a constant velocity v0. The next position-time diagram shown at the top here shows a downsloping straight line, starting at an original position x0 and then eventually adopting negative position values. This is an example of a point mass moving in the negative x direction. The position function in this case is given by x0 minus v0 times t. Differentiating this position function, we obtain dx on dt is equal to minus v0. The diagram at the bottom shows a curved line in the position-time diagram, and the question arises what type of motion this is. Since the slope of the curve increases with time, the magnitude of the velocity increases with time. This we understand as acceleration. While we understand acceleration intuitively, we only have to look to Newton's second law to find a definition of it. In the form appropriate to kinematics, Newton's second law reads acceleration a, in one dimension, is equal to the time derivative of velocity. Within calculus, this means that the instantaneous acceleration a of t is equal to the slope of the velocity versus time curve at the time t, as represented by the tangent to the curve at this time. As with velocity, acceleration is a limit, with delta t, the time interval, tending to 0. The limit of the velocity difference v of t naught minus v of t prime divided by the time interval. In other words, the time derivative of velocity. The fraction v of t naught minus v of t prime divided by the time interval is also defined as average acceleration over that time interval. This is equivalent to the definition of the average velocity. The quantity acceleration thus tells us the rate with which velocity increases or decreases per time interval. Instantaneous acceleration tells us how the velocity changes at a particular point in time. We can now relate position x of t, velocity v of t, and acceleration a of t with each other. These equations are known as the equations of motion. Acceleration is the time derivative of velocity, which again is the time derivative of the position function. Consequently, both acceleration and velocity are time derivatives of the position function, whereby acceleration is the second time derivative and velocity is the first time derivative. This is an important result. If, for a particular type of motion, we know the position function x of t, we can immediately obtain from these equations of motion the instantaneous velocity v of t and the acceleration a of t by differentiating with respect to time. Let us apply the equations of motion to a couple of examples. A bobsleigh may be running on flat horizontal ice, which might occur just before breaking at the end of the ice canal. In this case, the position function x of t is given by the product of the constant velocity v0 times t. Differentiating once with respect to time gives the velocity function, which in this case is equal to v0, which is the constant velocity. Differentiating again gives the acceleration function. Since v0 is constant, we obtain 0. Both results are in agreement with the inertia principle and expected. The motion is uniform, therefore we have a constant velocity and no acceleration. In a different situation for the bob, as illustrated here, the position function x of t may not be known. However, instead, the velocity v of t and the acceleration a of t are known. This might occur when the bobsleigh accelerates uniformly on the initial ramp just after the riders have boarded it. At this point of the race, the bob has an initial velocity v0 because of the manual push by the riders just before boarding, and over this straight downward section, the acceleration a of t is constant because it is simply due to gravity. Again, we can apply the equations of motion. However, in this case, we do not differentiate, we integrate. The velocity function is the time integral over the acceleration, which in this case is acceleration a, the constant acceleration a times t, plus an integration constant. The question arises, what does this integration constant represent? Dimensional analysis helps us here. It shows that the dimension of this constant is the dimension of velocity, and we interpret this as the initial velocity v0, just after boarding by the riders. We also want to know the position function of the bob, x of t. Again, we integrate. This time we integrate over the velocity function. A moment ago we obtained the velocity function as a0 times t plus the initial velocity v0. Integrating this over time gives us 1/2 a0 t squared plus v0 t plus a further integration constant. Again, dimensional analysis tells us that this has the dimension of length, since on the other side of the equation we have the position function x of t, which also has the dimension length. The position function of this accelerated motion is therefore 1/2 a0 t squared plus v0 t plus initial position x0. We see that if acceleration a0, initial velocity v0, and initial position x0 are known, the position x of t can be calculated for every time t. The free fall is an example of a motion with constant acceleration, in this case due to gravity. In a motion with constant acceleration, equal displacements are passed in faster and faster times. The relationship between position and time is quadratic. It is instructive to apply the equations of motion of kinematics to the example of a vertical projectile. I've quoted the equations of motion here once more. A of t is the second time differentiation of the position function, and v of t is the first time differentiation of the position function. And we might imagine a Scottish rock hurler throwing a stone vertically up into the air, and then hopefully stepping aside when it comes down. In order to make the problem a little bit more interesting, we might imagine that the launch of the projectile occurs from an elevated position h. The stone moves straight upward, and since this occurs on Earth, the only acceleration present is that due to gravity, minus g. What is the position function? We can represent this situation in a coordinate system with just one dimension, which is the y direction, and we define the ground as 0. The positive y direction is thus upward. The initial position is the elevated height h, and the initial velocity v0 is positive. The acceleration due to gravity is directed downward. Finally, we represent the rock by a point mass m. For clarity of understanding, let us also define some actual parameters. We might neglect the height of the rock hurler, but define the elevated position h as 10.0 meters. This is quoted to 3 significant figures. Also, the initial velocity v0 as 5.00 meters per second and gravity as 9.81 meters per second squared. Applying the equations of motions gives us the acceleration, velocity and position functions. Acceleration is equal to minus g, velocity is equal to minus g times time, plus the initial velocity v0, that's the launching velocity, the speed with which the rock hurler launches the rock upward, and finally the position function as minus 1/2 gt squared plus v0 t plus the elevated height h. This is a powerful set of equations that permits the calculation of many parameters associated with this type of motion. We may be interested in the maximum height of the stone, which is also the turning point. We can calculate this from the velocity function. Since at this time t, the turning point, the stone is briefly at rest. Therefore, the velocity function v of t maximum is equal to 0. That is equal to minus g tm plus v0. Rearranging gives for the time tm the ratio of v0 divided by g. Substituting with our numbers, we obtain a result of 0.510 seconds. In our case, the stone reaches maximum height and turns downward after 0.510 seconds. In order to calculate the maximum height reached, we can substitute the time tm equal to v0 on g into the position equation. That's shown at the bottom here. We obtain for the maximum height ym minus 1/2 g tm squared plus v0 tm plus h. Simplifying this, we obtain v0 squared divided by 2g plus h. Substituting with our numbers, this turns out to be 11.3 meters. After turning at the maximum height, the stone will fall downward and pass the launch position at h. We would like to know the velocity and speed when passing the original launch position. At this point, the position function adopts the value h. If we substitute h in the position function and call the time when the stone passes the launch position tp, we can show that 1/2 g tp squared is equal to v0 tp. Rearranging gives for this time tp the ratio 2 times v0 on g. Substituting in the velocity function, we finally obtain for this velocity minus 2v0 plus v0, which simplifies to minus v0. In other words, the velocity on return, when passing the launch point h, is the negative launch velocity v0. The sign has changed. This is of course expected because now the rock falls down. Interestingly, it falls down at this position with the same speed that it was launched with. Substituting with our actual numbers, we obtain for the velocity on falling down past h, v of tp is equal to minus 5.00 meters per second, and the speed is the absolute value of that, which is 5.00 meters per second. At what time will the impact on the ground occur? On impact, the position function is equal to 0 because we've defined ground as the 0 of the coordinate axis. Setting the position function to 0 gives us a quadratic equation. 0 equals t impact squared minus v0 g times t impact minus 2h divided by g. We can solve this quadratic equation in the standard way with the solutions given by t12 equal to minus p half plus minus the square root of p squared on 4 minus q. P is in this case equal to minus 2v0 on g, and q is in this case minus 2h on g. Substituting with this gives the two solutions as v0 on g plus minus the square root of v0 squared on g squared plus 2h on g. Using the actual numbers, we obtain the two results 2.03 seconds and minus 1.01 seconds. The negative result is mathematically correct, but it is clearly not a physics solution, since time always has to be positive. So the correct answer is the impact time is 2.03 seconds. We can also work out the impact velocity by substituting the impact time in the velocity equation. We obtain v of t impact is equal to minus g in brackets v0 on g plus the square root of v0 squared on g squared plus 2h on g plus v0. This simplifies to the negative square root of v0 squared plus 2hg. Substituting with the chosen values gives an impact velocity of minus 14.9 meters per second. During the entire motion, the acceleration is due to gravity. It is equal to minus g and constant in magnitude and direction. It is interesting to graph the time functions of acceleration, velocity, and position. That is shown here. The acceleration is due to gravity, negative and constant. The time diagram just shows a constant line intercepting at minus g. The velocity is first positive, starting at the launch velocity v0, and then decreases as the stone approaches the turning point. At the turning point it's briefly zero, and then becomes negative because the velocity vector points downward. Beyond the turning point Tm, the velocity remains negative and increases in magnitude until it reaches the magnitude of the launching velocity. At that point, the stone passes the launch point. As it falls down further, the negative velocity increases further in magnitude until it reaches the impact speed. The position function is an inverted parabola with an apex at the time at which the turning occurs, Tm. The original position of the stone is the launching height h, and at impact it has reached ground at 0. It is apparent that the three diagrams completely describe the motion of a vertical projectile. In the case of constant acceleration, the three equations of motion, the position function, the velocity function, and the acceleration function, are complemented by two other useful equations. They are shown here. They both relate the final position and the initial position to the final velocity and the initial velocity. In the first case, the equation also contains the acceleration, that is constant, and in the second case it contains the time. Both equations can be derived since with constant acceleration the velocity changes linearly with time according to v equals at plus the initial velocity. This can be rearranged to give acceleration is equal to v minus v0 on t, or vice versa, t is equal to v minus v0 on acceleration. These two results can then be substituted in the position function to give these complementary two equations. The first of these two equations is useful when the initial and final velocities are known, but not time. Its derivation is shown here. Substituting in the position function for time with v minus v0 on a gives x equal 1/2 a times in bracket v minus v0 on a squared plus v0 times in bracket v minus v0 on a plus the initial position x0. This equation can be rearranged and simplified so that x minus x0, the difference of the final and initial position, times a, equals v squared half minus v0 squared half. Rearranging once more, we obtain the desired equation with 2 times acceleration times the difference of final and initial position is equal to v squared minus v0 squared, which is the difference of the squares of the final and initial velocities. The position is thus given as 1 over 2a times the difference of the squares of the velocities plus initial position x naught. Let us apply this equation to our example of the vertical projectile. With the parameters defined as gravitational acceleration equals minus 9.81 meters per second squared, initial velocity v naught equals 5.00 meters per second, and the impact velocity that we calculated earlier as minus 14.9 meters per second, and a height of the launch of 10 meters, we obtain for the impact position 0 meter. This is indeed the ground where we expect the projectile, the stone, to impact. The second complementary equation in the case of constant acceleration is useful when in a problem the initial and the final velocity are known, but not the value of the constant acceleration. This equation can be derived by substituting for acceleration with v minus v naught on t in the position function. That is shown here. We obtain x minus x naught is equal to 1/2 in brackets v minus v naught on t times t squared plus v naught times t. Simplifying this equation, we find that the difference of final and initial position is given by 1/2 times in brackets v plus v naught times t. The position of a projectile can thus be calculated if the initial position, the final velocity, and the initial velocity are known. Applying this equation once more to our example of the vertical projectile, we show again that the impact occurs on the ground at a position of y impact which is equal to 0.00 meters, now quoted to 3 significant figures. We've used the parameters of an initial velocity of 5.00 meters per second and the final velocity v and impact time t that we calculated earlier as minus 14.9 meters per second and 2.03 seconds. The launch height was again 10.0 meters. The one-dimensional kinematics equations are therefore velocity v is the first time differential of x and acceleration a is the second time differential of x. This can also be expressed through integration as x equals the time integral over velocity and v equals the time integral over acceleration. Acceleration is typically a function of time. In the case of no acceleration, we obtain the familiar equation x equals vt plus initial position x naught, and the velocity is constant. In the case of constant acceleration, the position function is given by 1/2 constant acceleration times t squared plus v naught t plus x naught. Velocity is linear with it being given by a naught times t, and a is constant. As we've shown, we've got two complementary equations that are x minus x naught, the difference of final and initial position, which is equal to 1/2 v plus v naught times t, and v squared minus v naught squared, the difference of the squares of the final and initial velocity, which is given by 2 times acceleration times x minus x naught in brackets. This complete set of equations permits the solution of every one-dimensional kinematics problem. With an understanding of one-dimensional kinematics, it is straightforward to approach two-dimensional kinematics. The key to this generalization is the fact that the spatial components of the motion vectors are independent of each other. This is illustrated for the velocity vector. In 2 dimensions, the velocity vector can be split into a vx component pointing into the x direction and a vy component pointing into the y direction. The velocity vector is therefore the vector sum of these 2 components. Since these components have otherwise no functional relationship apart from containing both the shared parameter time, one-dimensional kinematics can be applied to both of them separately. This fact that vectors in mechanics combine linearly according to the rules of vector algebra is implicit in the 3 Newton laws. Sometimes, however, this is referred to as a further postulated law, called the principle of linear superposition. It is instructive to look at a real-life situation, such as, for example, a horizontal throw off a cliff. This is illustrated. The throw is a combination of 2 independent motion components. The horizontal motion is a uniform one-dimensional motion, fully defined by the initial throw-off velocity Vx0. The vertical motion is a uniformly accelerated one-dimensional motion due to gravity. Since the throw is horizontal, the initial vertical velocity Vy0 is 0. The vertical motion gains, however, speed in the negative y direction due to gravity. Combining the horizontal and the vertical motion, one can calculate the total velocity vector v as vx times the I unit vector pointing in the x direction plus vy times j unit vector pointing into the y direction. The sketch shows the velocity vector and its two components at one point of the trajectory. Along the trajectory, all three velocity vectors change. As time proceeds, however, the velocity vector is always the vector sum of its two components. This experiment demonstrates the independence of the horizontal and the vertical components of motion. Let us illustrate this problem further with defining some actual values. The horizontal launch velocity v0 may be given by 5.00 meters per second in the x direction and 0 into the y direction, and the launch may occur at a height of 10 meters. The initial position vector is then given by 0,10.0 meters, and the position vector after 1 second can be calculated as 5.00 meters, 5.10 meters. Both vectors are drawn in this sketch. That also shows the displacement vector, which is the difference between r1 minus r0, which can be calculated to be 5.00 meters, minus 4.91 meters. Substituting in the velocity equation gives for 1 second a velocity of 5.00 meters per second, minus 9.81 meters per second. Indeed, gravity will accelerate an object from rest over 1 second to a speed of 9.81 meters per second. During the entire motion, the acceleration due to gravity will be constant and equal the vector 0, minus 9.81 meters per second squared, constant in magnitude and direction. Since the components of motion vectors are independent from each other, apart from the shared variable time t, the components can be combined to provide information on interesting parameters such as range r of a projectile or the position of the apex of a trajectory. The sketch shows the launching velocity of a projectile and its two components Vx0 and Vy0. The three vectors form a rectangular triangle. Defining a launch angle θ0, which is the angle between the direction of the projectile and ground, one can express the components of the velocity in terms of the total velocity v0. Vx0 magnitude is equal to the magnitude of the launching velocity times the cosine of θ0, and Vy0 magnitude is equal to the magnitude of the velocity vector times the sine of θ0. Since the components are independent of each other, two equations of motions can be formulated for the position. The x position is given by Vx0 times t plus x0, and the y position is Vy0 times t minus 1/2 gt squared plus y0. This of course assumes that the only acceleration present is that due to gravity g, which points downward. A typical example of such a situation is a cannonball, however not considering drag on it. The launch position may be chosen as the origin of the coordinate system. Therefore, x0 and y0 are equal to 0. In the top left corner, the position, velocity, and acceleration functions of the cannonball are written down using vector notation. These three vector equations and 6 component equations completely describe the motion of a cannonball or any other projectile under gravity. They therefore also permit the calculation of the range r. The range r is reached at the time when impact occurs. The impact time ti was calculated earlier, for a one-dimensional vertical projectile motion as Ti equals v y naught on g plus the square root of v y naught squared on g squared plus 2h divided by g. Since in this case the initial y position, h, is equal to 0, the expression simplifies to 2 times v y naught on g. Since in two-dimensional kinematics the motion components are independent of each other, this result obtained for one dimension can be directly applied. Substituting the impact time Ti in the position function for the horizontal direction gives, for the range r, Vx naught times 2 times Vy naught on g. Using the expression on the previous slide, star, this can be expressed in terms of the launching angle theta 0, and the range is therefore V naught squared on g times the sine of 2 theta naught. The derivation also used the trigonometric identity 2 sine alpha cosine alpha is equal to sine of 2 alpha. Combining the information from the two components of motion, we can also show that the trajectory of a projectile is parabolic. Rearranging the x component of velocity shows that time is always x position divided by the x component of velocity, x on vx. Substituting this in the position equation for the y component gives y is equal to vy naught on vx naught times x minus 1/2 g on vx naught squared times x squared. This is the equation of an inverted parabola. It becomes even more apparent if we comprise all the constant parameters into the constants c1 and c2, so that y is equal to c1x minus c2x squared. The sketch shows the position component y is a function of position component x, and the trajectory is drawn. The apex at its center can be calculated by differentiating y with respect to x, dy dx, and setting that equal to 0. This is equal to c1 minus 2c2x apex. Substituting with the actual parameters, we find that the apex is at 1/2 v naught squared on g times the sine of 2 theta naught. As one would expect, the calculated apex x apex is half the range of r that we calculated earlier, since a parabola is symmetric. The question arises what maximum range r max can be achieved, and for what launch angle theta naught this occurs. We calculated earlier that, in general, the range is given by v naught squared on g, which is constant, times the sine of twice the launching angle theta naught. This sine function adopts its maximum value 1 when its argument is 90 degrees, and that occurs because of the factor 2 when theta naught equals 45 degrees. A launching angle of 45 degrees always gives the maximum range, which is given by v naught squared on g. All other ranges, less than the maximum range, can be achieved with two different launch angles. That's illustrated by the sketch. These two angles are complementary and add up to 90 degrees. This demonstration experiment illustrates the situation well. It also shows the independence of the vertical and horizontal motion. This can be understood when imagining that gravity would be switched off briefly. In this case, the falling object would stay at the top, and because the projectile points directly at that object, it will definitely hit it. Now, switching on gravity again, we realize that both the projectile and the falling object are affected by the same acceleration due to gravity. Because of that, since the trajectories will eventually intersect, they are also bound to arrive at that point of intersection at the same time and collide. This will always work as long as the projectile points directly at the target before release. It is straightforward to generalize the kinematic concepts and equations of motions to 3 dimensions. They are given as velocity is equal to the first time derivative of the position vector, and acceleration is the second time derivative of the position vector. This can also be expressed in integral form, as r being the time integral over velocity, and velocity v being the time integral over acceleration a. Acceleration is in general a function of time. In the case of a constant acceleration vector, these three equations take the familiar forms that are shown inside the blue frame. The position vector becomes 1/2 a naught t squared plus v naught t plus r naught. The velocity vector is equal to a naught t plus v naught, and the acceleration vector is constant in magnitude and direction. These equations apply, for example, to a cannonball that is fired into a strong transverse breeze, as sketched in the diagram. In this case, we not only have the parabolic trajectory in the xy plane, but a constant vz component of velocity that pushes the cannonball in the z direction. This situation is fully described by the three vector equations for acceleration, velocity, and position that can be expressed in terms of their 9 component equations that are shown on the right of the diagram. Comparing the illustration from 1561, based on Aristotle's physics, which suggests that the unnatural motion of the cannonball follows a straight line until its energy is exhausted at point F, to then be overcome by its natural motion and to fall straight down to the ground and find its natural place. Comparing this idea of motion to the kinematics description that has just been developed, it is clear that kinematics, based on Newton's laws, gives a much better description. Environmental effects such as drag can be readily incorporated to detail this description further. This, however, requires an understanding of the concept of force. Kinematics describes motion and trajectories in terms of time, accelerations, and velocities. It does not ask the question, what causes these accelerations? For example, the acceleration due to gravity is due to the gravitational force. This force and other forces are discussed in dynamics.